In this video, we will learn the use of hydrogen gas in chemical reactions in the presence of a transition metal as a catalyst. Hydrogen gas, H2, in the presence of a metal catalyst such as palladium, platinum, or radionickel is used for the reduction of nonpolar unsaturation, alkenes and alkynes, but can also be used for reduction of polar unsaturation, aldehydes, RCHO, R2CO ketones, CN-nitriles, NO2 groups. Important note, in most of the cases NO2 group reduces under mild temperature and 1 atmospheric pressure, but other polar unsaturation groups need high reaction temperatures and or high pressure hydrogen gas. As you can see various examples below, in example 1, it reduces both the double and triple bond together without any selectivity, and its addition to the double bond is syn addition. It does not affect the keto group under normal condition. It reduces nitro to amine, and under high pressure hydrogen gas it reduces cyano to amine. Highly important, the carbonyl group in carboxylic acids, COOH, and esters, THOA, does not undergo hydrogenation with H and PDOC even at high temperature or pressure. For example, benzoic acid converted selectively into cyclohexane carboxylic acid using a 5% PDOC catalyst under 6.89 MPa-H at 493 K. In such cases, homogeneous catalytic systems were developed, which are basically transition metal complexes, RU, IR, PD, RH, etc. Examples are given below. From the previous slide, we learned that carbon-carbon unsaturation is more reactive toward catalytic hydrogenation than other functional groups, such as aldehydes, ketones, nitriles, and nitro groups. The order of reactivity of carbon-carbon double bonds is more pronounced for less substituted alkenes than for more substituted alkenes, as shown below. Chemoselective hydrogenation. How will you reduce the olefinic double bond in the presence of other reducible groups such as NO2, CN, keto, or aldehyde? The answer is Wilkinson's catalyst IH, Cl-PPH3, 3. This catalyst is known for reducing the double bond without disturbing the other reducible groups. This catalyst is soluble in the reaction medium, so this hydrogenation is homogeneous. This selectively reduces the terminal double bond over the hindered double bond. Hence, it is regioselective as well. Stereospecific. CIS alkene on hydrogenation gives mesocompound, since the product is planar symmetry, while transalkene gives mixture of enantiomers, DL. My own mathematical analogy to remember it: if the compound has CIS geometry and reactions is CIS addition, then use this math. CIS minus CIS is equal to 0. It means no optical rotation I.E mesoproduct will form. Example, H2 addition, epoxidation. Otherwise, racemic mixtures or enantiomers. If the compound has trans geometry and reactions is trans addition, then use this math. Trans minus trans is equal to 0. No optical rotation I.E mesoproduct will form. Example, Br2 addition. Otherwise, racemic mixtures or enantiomers. Stereoselective. If the substrate has a chiral center, then it can direct the transfer of a hydrogen atom to the reactive functional group to give one diastereomer in excess over the other. For example, in case of keton having alpha chiral center 2 cases are there. Fig. A showed. Preferred conformation of ketones having a chiral center adjacent to the carbonyl group. Carbonyl group and large group on the chiral center lie in same plane. Hydrogen atom transfer from small group side, IS. Fig. B showed preferred conformation of ketone shaving a chiral center containing a group capable of hydrogen bonding with the adjacent carbonyl group lie in the same plane.